Yeah, no, I'm recording. I don't know what I'm doing, guys. Just so you know. All right. So today, like I said, we'll be looking at nucleophilic acyl substitutions, and hopefully it will be a review of what you've already watched in lecture. So what we want to do with this time is really just review the two main ways that we can see nucleophilic acyl substitution. Right? So for nucleophilic acyl substitution, you'll generally see this occurring under basic condition, or you'll see it occurring under acidic condition. Right? So basic or acidic condition. And our basic condition is the mechanism or conditions that is a bit more intuitive. It's a lot faster to write. The mechanism is a lot faster to write out. So let's look at our general nucleophilic, our general acyl species. So we're going to say we have R, and then we have C double bond O, and then some leaving group, which we'll write as LG. So our acyl species we'll consider to be our carbonyl adjacent to a leaving group, right? And this leaving group will change as we look at different functional groups. We'll have different leaving groups, but this acyl species is really indicated by the carbonyl next to the leaving group. And in basic conditions, we'll normally have a nucleophile, which has a negative charge or some extra electrons present. And our nucleophile will attack our carbonyl and push electron density to our oxygen, right? We're adding a bond to carbon, so carbon needs to lose a bond. We don't want a carbon with more than 4 bonds. And the best atom in our molecule to accept those electrons will be our oxygen. So in this case now we have R, C. Our oxygen has a negative formal charge. We have our leaving group, and we've added our nucleophile, and we'll call this species our tetrahedral intermediate. Right. So we have a tetrahedral intermediate, and our oxygen now has a negative formal charge that we can get rid of by allowing it to share electrons with carbon once again, which forces the carbon to lose a bond. And we're going to lose the bond with our weakest base. And in this case, it'll be our leaving group. Since we have our nucleophile is a good base, our leaving group must be a worse base. And now you can see that we've regenerated our acetyl bond O carbonyl, and we've added our nucleophile, and this would be our final product in basic conditions. Any questions there so far? No? Awesome. So that's basic conditions. That's the faster mechanism, like I said. In acidic condition, things are a little bit different. So we'll still start off with R, C double bond O, leaving group. But in this case, we're in acidic condition, so we're going to use HX to represent a generic acid. And we're also going to say that our nucleophile has a proton as well, which allows it to be neutral, right? So we have a neutral nucleophile, or a much less basic nucleophile, and we're using an acid to kind of allow this reaction to occur more readily. So in the presence of our acid, what will happen is we still have lone pairs on the oxygen of our carbonyl, and that can act as a nucleophile to deprotonate our acid and generate the conjugate base HX. So in this reaction, we see that we have R, C, O. This now is a hydrogen and a positive formal charge. We haven't lost our double bond, right? We have a leaving group present, and now we've also generated X minus, and we still have our, I'm actually going to write X minus in a slightly different position just so it's out of our way. We have X minus generated, and we also still have the presence of our nucleophile, NUH with a lone pair. So now our nucleophile, since we've actually activated our acyl species now, so it's activated, we can allow our nucleophile to attack our carbon in the acyl group, and then we'll push electron density to our oxygen. So this now allows us to generate our tetrahedral intermediate, where we have OH, we have a leaving group, we have our nucleophile that's added. Remember that our nucleophile is, we're thinking of it as a protonated species. So in this case, now our nucleophile gets an extra bond, which gives it a positive formal charge. And between our nucleophile and our leaving group, in our acidic condition, we'll say that our leaving group has a better affinity for protons. So our leaving group will take our proton away from our nucleophile to get rid of the formal charge on our nucleophile. Right. So now we generate, from this tetrahedral intermediate, we generate RCOH. We have our leaving group, which now has a hydrogen and a positive formal charge. Our nucleophile is now deprotonated and neutral. And we want to basically allow our nucleophile to get electrons. So if we're giving electrons to our nucleophile from carbon, that's the only option to provide our nucleophile with electrons, then we can use the electrons in our carbon-oxygen bond to allow carbon to have 4 bonds once again. So this allows us to generate R, C, double bond O, H. Now oxygen has the positive formal charge. Our nucleophile has been added. We've generated our protonated leaving group, right? And then the final step is, as you remember from basically our first step, we generated a conjugate base species that can now be used, X minus, to deprotonate our oxygen and our acyl species. And this allows us to re-add a lone pair onto the oxygen, right? So now we've generated our nucleophilic acyl substituted species. We have HLG generated, and we've also regenerated our acid, which we can consider to be basically a catalyst. Right? So we have all 3 of those species, but this is kind of the desired species that we want right here. This is what all that work was for. All right, any questions? No? All right, so now we're going to go through 2 examples, and we'll look at carboxylic acid specifically as our nucleophilic acyl species, and we want to get some substitution there. And I like to call these examples pseudoacidic acyl substitutions because they look similar to our acidic mechanism. I'll just go back to that really quickly. They look similar to our acidic mechanism, but the main difference here is that we're going to do something slightly different. Instead of having an external acid that can protonate our acyl group to activate it, we'll actually use a proton that's already present in our molecule. So let's talk about how that works with a carboxylic acid. So for our carboxylic acid, our general carboxylic acid, we have R, C double bond O, OH. And we can take a carboxylic acid, and if we want to take our carboxylic acid and generate an acyl chloride, we can use SOCl2 in the presence of TEA or pyridine in order to generate an acyl chloride. That's one way we can halogenate or do a halogenated substitution. Another halogenated substitution can be done with bromine. So we'll take our same carboxylic acid, but now we'll use PBr3 in order to generate an acyl bromide. So this would be, if we put our names in, this is an acyl chloride. This is our acyl bromide. And I kind of want to go through the mechanisms for both of these species. So if we were to draw the Lewis structure for SOCl2, so we'll start off with the first reaction to generate our acyl chloride. And if we were to draw the Lewis structure for SOCl2, we'll get SO, Cl, and Cl. And we want that to react with R, C, OH, double bond O, and then the oxygen there has 2 lone pairs. And what we're saying is we will treat our electron density from our oxygen, and that will attack sulfur, and we'll push electrons to oxygen here. We see that we have this oxygen acting in a nucleophilic way with sulfur, or really it's more of the electron density from the bond itself. And then this, because we're adding a bond to sulfur here, sulfur needs to lose a bond, and that gets pushed to oxygen, our more electronegative, or sorry, the electronegative element, oxygen there. And then also, since we have, so the reason why we're considering this arrow to actually come from our carbon-oxygen bond is because we want to provide this carbon with more electron density. And we'll do this by now saying that we have our carbon is still there. We've made a carbon-oxygen double bond here. And now to this oxygen, we've added a sulfur that now has another oxygen with a negative formal charge and 2 chlorines. So this kind of looks a little bit funky. We may want to redraw it. So we'll redraw just so that it's a little bit easier to draw our electron pushing arrows. So now we have R. I want my COH to be to the top. That way the larger functional group OS double bond, sorry, single bond O minus Cl. Sorry, this should only have one Cl. Cl is present there. And then as we push electrons back down, we'll generate Cl. So now we have R, C double bond O, H, positive charge. And now we have O, S, double bond O, Cl. And then we've generated Cl minus, which is our good nucleophile. So our good nucleophile can now attack our species, push electron density to oxygen, giving us R, C, single bond OH, and we have Cl, O, S, double bond O, Cl, right? And in this case, we'll see that our oxygen has 2 lone pairs, and we've generated a really good leaving group. So as we regenerate our double bond here, we'll lose our OSOCl species. And as we take electron density from this carbon-oxygen bond, we'll also, since we're adding a bond between oxygen and sulfur, sulfur is getting a new bond, so it needs to lose a bond, we'll generate another equivalent of Cl minus. So now we have R, C, double bond OH with a positive formal charge. We've added our Cl, and we've generated S, double bond O, double bond O. We also have made Cl minus. And now the chlorine that we've generated can deprotonate our activated species. And I want to use reversible arrows to generate my final chloride species. I've also made HCl and SO2. And the reason why we include TEA, tetraethyl ammonium, or pyridine, is so that we can actually have a reaction here. So it reacts with TEA. And since this is basically, we're treating this as pseudo-acidic condition, we want to get rid of the acid that we generate. So we want this acid, HCl, to be eliminated from our reaction. And that occurs when we have TEA present.